take a time and go ahead and start working through these. So these problems here, again, as I mentioned, the purpose of them is just us to kind of review what exponential, and we'll look at logarithmic functions as well as kind of what are these are as far as the algebra behind them. Okay, but we also need to jump into the calculus perspective. All right, how do we deal with this from a dealing with like limits or derivatives? Okay, as we go through the next couple of days, so today and Wednesday, we're going to kind of look at the foundation of both. Making sure we review the basics of algebra. How do limits help us? How do derivatives help us? And we'll look at the limit definition of derivatives for these functions as well. As far as the functions are concerned, just make sure you're comfortable with handling the exponents that you're plugging in. Okay, so like making sure to see here, hey, that's 2 cubed. So when we do the order of operations, we'd say, hey, that's 3 plus 8, which is 11. Watch your signs, as we've always talked about. Be careful with that one. So like the g of x here has a negative on the outside. So as far as order of operation is concerned, it's telling you do the exponent and then multiply by -1. So this, in this case here, we would have -1 times 3 to the -1 plus 2, which will be -3 when we're done. Other ways that problems can be like this can be written would be like, say, 9 minus 3 to the x plus 2. The parentheses may not be there, but the idea is, hey, I'm going to use the exponent first, and then we'll deal with the negative, which in this type of problem would be focused on subtraction. So definitely watch for stuff like that. Especially if it's not something you've seen in a while, right? We'll always want to look for that. Now, as a quick review, why would we plug in 0 again? What does plugging in 0 give us? Y-intercept, right? So don't forget little things like that. Plugging in 0 gives us the y-intercept, setting it equal to 0 to give us an x-intercept, okay? With that said, what does 2 to the 0 equal? That's another one we need to make sure to review. And we haven't seen in a while. Anything to the 0 as an exponent is 1, okay? So what we'll see here, f of 0 will end up equaling 4. But be careful with g of 0, because that's going to end up being -3 squared or -9. Any concerns with just plugging stuff into exponential functions? All right. Now, what you're going to find is these equations that I set up over here, one of the things we would be more straightforward would be setting them equal to 0. What happens with exponentials, all right, we get to situations where they don't work out nicely. Like if I said 2 to the x equals 5. Well, this isn't necessarily going to work out nicely, because when we start thinking of powers of 2, 5 isn't one of those. All right, if we try to plug in, like, say, something like x equals -1 or x equals 0 or x equals 3, we would have 1/2, 1, or 8. We can work those out nicely. Okay. 5 isn't going to be a power of 2. So that's where logarithms will end up helping us in a little bit. But I made these equations, though, to where we can definitely work them out. So what you'll see here, this will be the -3 to the x plus 2 equal to -27. All right, well, we can divide out the negatives, thankfully, but also see here that you can rewrite 27, hey, because that's 3 cubed. Doesn't always work out like that, but here it does work out nicely, right? I can rewrite 27 as a power of 3. One of the things that we're going to review when we look at the graphs is that exponential functions are what we call one-to-one. So remember, the vertical line test determined if a relation was a function. For each x, there's only one y that's associated to it. One-to-one took it a step further and just said, hey, for each x, there's only one y, but that's also true in the reverse. So every ordered pair is unique. No x value or y value is going to be repeated when we look at a one-to-one function. The reason we like that here is the only way to deal with this problem, if the bases are the same, which we have here, well, then the exponents must be the same. That's the only time that this is going to be true, is when those exponents are exactly the same. So because exponentials are one-to-one, I could just solve the exponents equal to one another. which would give us, hey, my answer should be 1 here. Any questions with that one? Right. The one thing I hope that you take away from that is that little side note that I made, right? If I put 2x equal to 5, it still has a solution out there, and we expect it to have a single solution because of the whole one-to-one perspective, but it does not always work out this nicely to where I can get to an integer or some rational solution, okay? With that said, let's get this out of the way and look at this next one. So if I set this equation equal to the 35, just make sure you see here the difference is I got to get that 2 to the x by itself. So subtracting the 3 from both sides would give us 32. And then immediately we'll be thinking, hey, how can I rewrite 32? Okay, if you ever get stuck, just do a factor tree. Well, 32 is even, so that's a good start. I could factor out a 2. And as you look at your factor tree there, if you go through that whole process, hey, everything I break out is going to end up being even here, and it's going to keep on going. What you'll eventually get to, though, is 2 to the 5th. Right? And from a factor tree perspective, you just count how many 2s that you had at the end of all those branches. Okay. But with that said, then, hey, my answer for this then is just going to be x equals 5. And the reason that we can say that is because, hey, exponential functions are 1-to-1. I know if the bases are the same, then the exponents must be the same.
So we just need to know what is the exponents that lead to 32.
Well, that's what we end up finding, yes. But the key is if I go up here and I go find f of 5, what is f of 5 going to equal? We have to remember where we started, right? F of 5 is going to equal 35. I can have that confidence because of the work that led there. Okay. Thank you. Any other questions or concerns I could help with? Now, keep in mind, it doesn't always work out nicely like that. I just use those as kind of quick examples of what some things I can try to do. All right. As we'll look at more on Wednesdays, just kind of reviewing how to handle the logarithms. Some of you might have had college algebra this semester before, some of you might not have had it right before this. So just a way for us to review. With that said, then we need to be prepared to graph things. Okay. Now, as far as some things that we can be prepared here for is, as I mentioned, the function is going to be 1-to-1. So that means it passes the vertical line test and the horizontal line test. That's nice to know. But we could also explore some stuff a little bit further. All right. First and foremost, the domain for exponentials is all real numbers. So that'll be one thing that's kind of helpful to keep in mind. Is that when I look at an exponential, the domain is all real numbers. So I don't have to worry about any restrictions. With that said, then we can definitely go look at the limit here. What happens is x goes to negative infinity of f of x. And what happens when x goes to positive infinity of f of x? These would definitely be some things that we need to be comfortable writing out that says, hey, when I want to discuss a function, these limits to infinity will help us to discuss what we call end behavior. All right, so hopefully you'll see here, I'm going to use those sum and difference properties we talked about. The -4 is a constant value, right? So the limit as x approaches any value, let alone infinity, will remain -4. So I just focused on the term that had the exit. Just make sure you see that's -4 plus whatever the result of this limit is. With that said, this is where making sure we remember some just basic rules of exponents will help us. Because what we're going to get here from trying to do direct substitution now would be -4 plus 2 to the negative infinity. Whereas the next one would be -4 plus 2 to the positive infinity. Okay. Now, the nice one here is the positive infinity. Positive infinity plus or minus 4 is still infinity. So make sure you see that going to positive infinity here. When my exponent is positive infinity, we're just going to call that infinity. What does that tell me about my graph? So if I do a quick little coordinate plane here, my graph over here, I don't know what it's doing, but it's going to grow forever without bound. If it was negative infinity, it would decay forever without bound, but we had positive infinity. So, hey, I know that's going to be the case over there. However, with that first one, I did negative infinity. If you use your rules of exponents, we can actually rewrite this as -4 plus 1 over infinity. Now, what happens is the denominator gets really big and we continue to grow it. As we look at that perspective, what did we say that this approaches? That approaches 0. This is definitely one of those things that we want to make sure to remember is like, hey, I can use this limit to tell me that that approaches 0. So the second one, hey, it's just infinity, and that's what we're going to call it. But this one is different because it approaches 0. But this goes back to exponents and then us using rules of exponent. Because it was a negative exponent, I can use the reciprocal of that. Okay. So it approaches 0, which is nice because if that approaches 0, this whole thing approaches what? That -4, that constant term, right? Make sure you see there was a constant. What that means then on this other side, this graph is going to continue to grow on the right side, but over here, it's going to start to actually flatten out. It doesn't actually get to -4. Remember, limits doesn't say that you're going to get -4. It just says that, hey, the number is going to be so indistinguishable, we might as well just call it -4. Okay. The difference will be so small that the limit can help us discuss what's going on over there. Remember, this is then going to be what we call a horizontal asymptote. All right, this is something that we looked at when we were talking briefly about rationals. Don't forget you have these things called asymptotes. This for us is a horizontal asymptote. We can use the equation y equals -4. And what we'll say is, hey, my left hand of my graph is bounded by this value. It will never cross nor touch this because of how exponentials work. Okay. Now that was a rough sketch. Please understand that. I'm not saying that that's our graph. That's just me showing you how we can use the in behavior to get started. Any concerns with that part? Now, with that said, then based on my quick sketch here before we actually get the graph, what's the range? Right? What do I put on the -4 though? Bracket this thing. Yeah, this one's going to be parentheses because we got it from a limit, right? That means I won't ever actually get to -4. So this is one of those ones where it's kind of tough, right? But this limit actually helped us explain that because I had to use the limit to get that value. That's why I'm going to use parentheses. I don't actually get there, but the limit helped me know what the value was. Okay. So as you hopefully see here is that, hey, from the beginning, know that exponentials have a domain of all real numbers. From there, I can take a quick look at the in behavior. If you remember from your college algebra class, it was plus 2 raised to a power and then positive x. So you knew it was growth from that perspective. Okay, that's kind of what we do in college algebra. Just know that, hey, it's growth. With that quick sketch, though, the limits help us kind of do a quick visual. Now we can go improve it moving forward. Okay. Are we good, though, from why I use the limits to get to the range and get a quick idea what the graph looks like? Now, I haven't got to the chance of grading it, but that packet I had you do the other day, this would be a good example of how can we improve our work on a packet like that. Well, let's make sure we show limits as x approaches infinity or negative infinity. That'll help better describe the behavior of our function, okay? I'm gonna slide this over though, because the next thing it wanted me to do is find my intercepts. So remember, as far as intercepts, we could just plug in 0. So we get, if I plug in 0, I get 0 plus 1, which is 1. So it's gonna be -4 plus 2. The other one though, remember, is gonna be set it equal to 0. So this first one was our y-intercept. This will give us our x-intercept. Now make sure you see here, I use -4 on purpose so that when I go to solve this and I add the 4 to both sides, how can we rewrite 4 to help us go further? Right, so because it was a power of 2, right, we definitely can deal with this. Just make sure you see as you go through and solve that, it's x plus 1 equals 2 is what we're gonna focus on. So we'll go to show that, hey, x equals 1 is our x-intercept, okay? From here, we can go get a little bit better graph of what we're dealing with, okay? Transformations is another great way to go through and graph this because it's a base 2. But what you're gonna find is, we're gonna talk about in a second, most often, we're not gonna have nice integer bases. We're typically gonna have something like a rational, or we're gonna use base E, as you might remember. Now, as far as the work was concerned here, identifying the domain range and intercepts, we were able to do from the front end. So that's nice. That's going to help us better get the graph. Are there any concerns though with the work I've done so far before we look at the graph a little bit better detail? Shrink this work down then. We'll zoom in a little bit over here. Yeah, as far as dealing with this graph, when you're graphing an exponential, the one thing I do recommend first is make sure you deal with that horizontal asymptote right away. As you work with these functions, do you technically have to do the limit every time to show that that's the case? Does everyone see where the -4 came from here? This is one of the reasons we're able to do a lot in college algebra. So, right, this right here is what we call a vertical shift from our previous experience, and that's going to be our horizontal asymptote, okay? Now, the key here is just make sure to know it should be on the left hand or the right hand of the graph. That's definitely a part we want to be careful with. From here, though, we did find our ordered pairs. We said 0, -2 is our y-intercept, and 1, 0 is our x-intercept, okay? The only other point here that would be nice to work with, sorry, y'all, would be this. Would be me putting that point here. This would be the only point that I could say that, is a good point to find. Where did I get the point, though, would be the question. Well, that would be me looking at this exponent here and remembering that, hey, for transformation purposes, that's where we would say we have a shift to the left 1. The -4 then would be a shift down 4. Well, the shift down 4 is captured by the horizontal asymptote. This shift left 1, though, is not actually here on the asymptote. This just goes back to remember that anything to the 0 exponent equals 1. That's why it's one above the asymptote here. Okay. From there, that's a good quick graph that we can use then to help draw what we're dealing with. On one side, it approaches -4. From here, it grows exponentially. Nothing's going to stop it. It goes to infinity. Okay. As far as if you want to deal with it a little bit further, this point here would be 1/2 up. This point here should be 1/4 up, and so on, 1/8, 1/16, and so on, all powers of 2. This side, it's 2, 4. If we wanted to go another one, I technically should have went higher here because it should have been at 8, because they're all powers of 2 from the horizontal asymptote. Okay, so it's nice here because we did a base of 2, but as I mentioned, we're going to deal with stuff that's like base E. Okay. Now, did that graph change a lot based on the sketch that I dealt with first? Not really, but it's more accurate based on from what I did the first time, right? Using just the limits, no, my domain was all real numbers. We got a quick sketch, but here we were getting a little bit more accurate with the curve by having the x-intercept and the y-intercept. Okay. When you can use transformations to locate this point here, all we're doing is better helping our accuracy. Okay. As you saw over here, this technically is not right. It should have been more up here. So even then I messed it up. It's not perfect when we do it by hand, okay? With that said, one thing I did notice, some of the papers I looked at, when it comes to that like sheet where I wanted you to print it off and work it out, you should be drawing your graphs by hand because that's what we're going to do on the test, okay? So if you didn't do that graph by hand for that sheet, make sure you go back and practice it so we're ready for these next tests. Are there any concerns though with how I brought the limits in to help talk about this exponential? Because that's definitely one thing I wanted to make sure to connect. We didn't really do any of these with limits. Are we okay with the quick review of graphing then? Any questions with this one before I go forward? All right, so the next thing then is just make sure we go in and get our calculators out and comfortable dealing with base E, Euler's constant. Here's one of the areas where in college algebra, you were just told this is what E is. But now that we've looked at limits, well, guess what? The result of this limit is where we get base E from. Okay, we're going to look at that a little bit when we get past derivatives into what we call integration. As we deal with base E, the natural base, sorry, that leads us to the natural log. Well, the natural log isn't quite what you were taught before. There's a little bit more to it. I didn't even learn about it until I started teaching this course when I saw it in the textbook. I don't remember anyone ever showing this, but we'll look at that, how it's not just something here, use it. There's a little bit more to it. But the main thing here that we do need to be comfortable with is, hey, I gave us a function with a base E here. Make sure you're able to go to your calculator, and we can practice now while we have a couple minutes with plugging this in and using your calculator to get an approximation to the second decimal place. As you go through there, as you practice your calculator, just make sure you're putting your parentheses in correctly so that you're getting to these values when you're done. Most of y'all have that TI 30, so make sure you're closing that parentheses, that whenever you do this, if I remember correctly, it's going to put E bracket, not bracket, sorry, your little caret and then a parenthesis. You want to make sure to put 0.09 times 5 and then close parentheses so that all of this is included with that operation. So be careful with how you type that in. Now, as far as formulas are concerned, does anybody recognize structure of this formula that you used in college algebra? What we used it for? One of the things I should say we used it for.
Okay.
It's a part of growth and decay. In this case, we'd call it growth though, because of the positive exponent, okay? But that would be one of those application problems. But another one to be a bit more specific. Well, they may have not used A of T. Kind of follows that pattern, right? This is a little bit more practical for us because this is compound interest, right? So from a business perspective, definitely need to be comfortable with like recognizing the compound interest formula, but ultimately it is exponential growth and decay. All right, the growth and decay depend upon whether you have reflections or not from a vertical or horizontal standpoint. One of the things that we will definitely have to be careful of in this class is always identifying, all right, are we looking at growth? Are we looking at decay? And how do we want to handle that moving forward? Is there any concerns with using your calculator though to get to those approximations I threw out there?
Yeah,
What did you get for 5 when you plugged it in?
I did not get anything.
All right, so with your calculator, make sure you're putting 250 and then your multiplication symbol. And then if I remember right, isn't it second and ln key or is it?
Yeah, second.
Yeah, so you're gonna hit second and then look for that ln of, I don't remember what it puts here though.
It is the E and then,
Well, I'm thinking about the key itself. What does it say? Ln of what?
LN.
Just ln. So your ln key. When you do that, it should look something like this, 250 times this. Is that what you're seeing? It has a parenthesis already though, right?
Yeah,
So put 0.09 times 5 and close that parenthesis to ensure that it's treated correctly.
0.09.
Times 5. That was supposed to be a multiplication symbol as well.
We would not do.
Oh,
Something is off on something. You have the right number. We should see what we do. It's like you're inside the musicians. So you probably have the right answers. It just looked weird.
Yeah,
Anyone else with concerns? Are y'all good over there with the Casio? And is that Casio too? All right. So here's some things that we can look at then is let's go graph this 5 minus e to the negative x, okay? And then you'll see here, let's go find the average rate of change, which is leading to what? A derivative, right? We started with the average rate of change and then we went to the limit definition of derivative. So no, that's where we're going. As far as graphing this is concerned, right? One point that is nice to work with is f of 0. Oops. Plugging in 0 is not bad because that's just going to give us 5 minus 1, which is 4. Because e to the 0 equals 1. Setting that equal to 0 is not going to be nice. All right, so we're not going to do this one here because it's base e. Because it's base e, that would force us into having to use logarithms to better understand those values, okay? The good news is if I ever need it, I can use logarithms or I can go look at the graph and approximate it, okay? We have different ways to get there, okay? The next thing then we can look at is the limits, all right? So the limit as x goes to negative infinity of f of x and the limit as x goes to positive infinity of f of x. With that said, make sure you see here, we should be expecting one answer to equal what? Not 4, the 5, right? But it's a constant value, right? The 4 just happened to be our y-intercept, okay? But one of our answers out of here should be 5. The other one is going to be infinity or negative infinity, all right? So keep that in mind. Whenever you deal with an exponential, one side's going to approach the asymptote, the other side's going to grow or decay. With that said, this is where paying attention to these is going to be important, okay? So when I go look at negative infinity here, I'm gonna have negative e to the negative infinity. Well, negative is a positive, right? So this in the end, e to the infinity is just going to be negative infinity. Okay, now keep in mind, if you want to write out all the work we did before, that's perfectly fine. But I feel like a problem here, you can kind of do a quick direct sub into where x is to kind of work it out. Be careful here, though. There was a negative in front of e, so this first one is actually going to go to negative infinity. Well, hopefully then what you heard before, we should know that this one goes to 5. But to show that, again, just do your direct sub into the e to the x part. So e to negative infinity was what we'd have there, which is -0, which is just 0. So that would confirm that, yes, this second one should be 5, where this first one is the infinity. But be careful, as I mentioned, it's negative infinity this time. Any questions or concerns with that? Now, moving forward, then we can go do a quick sketch of this graph. Why am I putting this here first? That is my asymptote, right? That's the whole reason we just did this piece here, right? Was to get to that asymptote. The whole reason we looked at limits of to infinity was, where's my horizontal asymptote? The good news is, though, y'all, we can have confidence knowing that it should have been 5 to begin with. If you didn't show the limits to infinity here, well, hey, I know I'm working with exponential. That 5 is going to represent my vertical shift. This is where the negatives come in, though, okay? Because the negative was in front of the e, my graph is going to be below that. Right? And that's because we have negative, sorry. That's because we have negative e to some exponent. Because of this negative, I know I'm going to go below the horizontal asymptote. Okay. Well, if you take the previous graph we did and just do that by itself, it would look something like this. But we also have a negative on our exponent, right? So that's what's going to say, hey, I actually need to take that and use a mirror image of this. So I'm going to use, I don't think it lets me do mirror images. Nope. We're going to use something that looks more like this, which gives us a growth model where it starts at negative infinity and works its way up. Okay. The good news is, though, as we looked at f of 0 equals 4 was one of the points we were looking for. All we can really do here, though, for this graph is draw it as such. Okay. Approximating the x-intercept could help you a little bit more, but as I mentioned, the way that we deal with that requires logarithms. So we'll deal with that at a later time. Well, the 5, this right here just tells us where to put this. Okay. Yes.
If at -5, one would be -5, one would be infinity. First is
Well, no, because that's a little bit different. Okay. Looking at this, you could have just did your graph and you're good. Okay. Does everyone like the way you're saying it? Hey, whatever I see here, I'm gonna go graph that and I'm good. This would only be -5 if this was -5. So what you would see is if I would just take this whole graph and shift it down if all that change was this. Okay, the reason the graph worked out this way is more because of these negatives here.
see how you got
Yeah,
f of x equals -infinity. If say the equation was -5 minus e,
yes.
then it would be -5 and then positive infinity.
No, it'd still be negative infinity. Because all that would impact would be wherever your constant term is. Okay. If you change this to a plus sign, then that would become a plus infinity. And then that right there would say, hey, it looks more like this. That help with that? I remember, hopefully you saw here, I was able to condense that work down and get a little bit more quick graph. I can't necessarily get more information here unless I just start plugging in random values for X. But everything then's going to be on a decimal approximation. Okay. So with that said, this was just a good quick sketch. If I want more detail, then I'm going to need to go talk about logarithms. And that's one of the things, as I mentioned, we will do that. What we want to do though is the average rate of change now. Okay, so what we will go find right now is f of 5 and f of 2. Now, as far as this graph is concerned, I know it's not perfect, but that means we're focusing here and here. Should our average rate of change be positive or negative as we go from f of 2 to f of 5? Should be positive, right? So whatever we do here, we better get a positive number. Is it going to be a nice number? Not really. Okay, not really. You can go get decimal approximations, or you could just plug it in and use it as it is. So let's just look at it from the perspective of using it as it is. We get 5 minus e to the negative 5, 5 minus e to the negative 2. Okay, you can go put those in a calculator, get a decimal approximation. Just remember, as far as the average rate of change is concerned, this is where y2 minus y1 all over x2 minus x1 is going to help us out. So we'll have 5 minus e to the negative 5 minus 5 minus e to the negative 2 all over 5 minus 2. Now, just kind of doing it real quick. Hopefully you'll see at the top, we distribute the negative 5s go away. So really what we're just focusing on is how do I handle the e to the negative 2 minus e to the negative 5, okay? This became positive though, because again, we distributed our negative. You may not like it doing this way, but understand I'm doing it on purpose because we're about to go do a difference quotient before we finish up. Make sure you see here, you should know that this is going to be positive because of the fact that when you have a negative exponent, that's a fraction. So 1 over e squared is bigger than 1 over e to the 5th. Okay, if the denominator is bigger, the fraction is smaller. So that's why, hey, when I do the subtraction in the numerator, it will end up being positive. And what you'll end up getting is something like 0.0429, just as kind of a quick approximation. Now, if you would have approximated up here, know that your answer should still be similar, but maybe not that exact value. Okay. The key here, though, is we should be making sure we get a positive value. That's definitely the important thing. Having a very small slope, does that make sense? Well, yeah, because that's pretty close to horizontal already. Not quite, but we're getting pretty close to horizontal. Right? And the further I go out with my approximations here, the closer and closer that should get to 0. Okay. Any questions though with me doing the subtraction and stuff to get there? Anybody want to take a picture before I swipe over? Now, hopefully what you saw, I just plugged in the 5, the 2, and I did the subtraction to get there. Let's use that to help us find the derivative now. So the derivative of a function, when we use the limit definition, is found by the limit as h approaches what? 0, right? What happens when those points get so close that the difference is pretty much 0, right? The difference is so small, it's as close to zero as we can get. Remember up top though, this is where we're gonna have f of x plus h minus f of x all over just h. With that said, the only thing we need to go find then is the fact that, hey, f of x plus h will equal e to the x plus h. Now, this is going to be a little bit different than some of the other limits that we've worked with because of what we're limited in how we handle it. Okay, so please understand that. The good news is it's not as bad as it seems. Okay, it's more just tedious at this point because what you're going to find here is let's go plug everything in. But rules of exponent is going to be what helps us. So e to the x plus h minus e to the x all over h. Which we can't do that subtraction. That's the part that I mean by it's tedious. And now it's not like a square root. Remember, square roots, we had to go multiply by the conjugate on top and bottom and simplify. What you'll see here, this is more about your confidence with rules of exponents. So what I want you to see here is that when you have e to the x plus h, well, if you had to add the exponents, that means you could use multiplication instead, that those things are interchangeable. When I do that though, what's nice about this numerator now? What do the two terms have in common? They all have the same base. That's important, but two of them have e to the x, right? Now with that e to the x, I'm not even worried about x right now. I'm focused on h. Everyone follow me on that? So technically e to the x, I'm going to treat like a constant multiple. So I'm going to say f prime of x equals e to the x times the limit as h approaches zero. Now keep in mind, we factored it out, right? So e to the h will be by itself. What should be after the negative sign though? Just one, good. Make sure you see here, since I'm factoring these out, don't lose that second term, but put a one, okay? Now, if you try to do direct substitution here now, you're gonna get one minus one, which is zero all over zero, which is an indeterminate form. That does not help us. You could try to break it down different ways, but you're always gonna run into indeterminate or some type of undefined situation, right? So if we get to something that we're not quite able to handle, what's another way to find a limit that we should not forget about? Table, right? Let's jump into a table. Now, I'm going to do it real quick because we're running out of time. But what you'll see here is I'm going to use h as negative 0.01, negative 0.001, 0.001, 0.1. And you could always add more as needed to help you see this. But these values are getting closer to what? Not one, to zero, right? What's the limit going to get closer to is what we're interested in, right? Now, if I had time, I would show you that I did this in Excel earlier. Excel makes stuff like this so much easier. If we had time, I would definitely show that. But just for the sake of it, since we are supposed to be done at this moment, give me 1 second. Just based on the one side, what do you think it's approaching? Looks like it's approaching one, right? So what we hope to see is a confirmation on the left-handed limit here. Now, keep in mind, I'm doing two different limits when I'm writing this out. I'm doing a left-handed limit and a right-handed limit. Based on those two limits, do you think we can be confident with that it should be approaching one? So if this approaches one, what's the derivative of e to the x? E to the x. It's a little bit different than what some of the other ones we looked at, right? E to the x, right? And the derivative of it gives us the same thing back. Okay. Now, as far as dealing with this one, we are stuck using a table approach right now. Another way that we can deal with that, we'd be able to talk once we get into more what we call anti-derivatives and such, and we can work through something, what we call L'Hopital's, okay? But for us right now, table approach, hey, that looks like it's approaching one. Hey, I like one because anything times one is itself. So the derivative of e to the x is e to the x. Just be careful for the chain. The chain will definitely impact this, okay? So please be careful with that. Any questions, concerns with doing this as far as the derivative is concerned? All right, so as I mentioned, then just be prepared for Wednesday when we jump in and we look at it from the perspective of dealing with